Hi, I'm Teresa Johnson from Google, and this is Mehdi and Amini from Apple. And today we'll be talking about ThinLTO. This is also jointly developed with David Lee at Google. ThinLTO is a framework for scalable and incremental link time optimization. And as what we hope to show you by the end of this talk, it brings us towards having a reality of always enabled LTO. But before I talk about what ThinLTO is, Mehdi is going to first give some background about LTO and talk about why we came up with something new.
All right. So what is link time optimization in the first place? So optimization is usually about performance. So let's see how we get those with LTO. So usually when you build a program from source file, Clang will generate intermediate object files specific to the platform. You can enable LTO by adding -f-LTO on the command line. The effect is that now the objects are no longer platform specific, they are raw bitcode files. Even though the extension doesn't change, those are still .o, you can manipulate them with the LLVM development tools, opt, LLC, and so on. So let's see at the big picture of a build flow with LTO. So the build system will spawn Clang in parallel and generate the intermediate object file, which are, in this case, LLVM bitcode. When you reach the linker, those bitcode files are opaque for the linker. It will need some help to handle those. It will invoke LLVM as a linker plugin. So LLVM will read those bitcode files, and the third thing it will do is merge all of these in a single module. This is the monolithic LTO implementation. We're going to have single-threaded optimization and inlining on this single module that contains a full LTO program. And when we reach the codegen, we generate the platform object file that we give back to the linker to resume the binary link. So why would you use LTO? So one of the first benefits is binary size. You can have better dead code stripping and internalization that will hide some symbol from tables. But the main driver is performance. A 10% boost is very common. Some application can even get higher performance benefits. The main reason is that LTO removed the cross-module boundaries. The optimizer can now optimize across file. For instance, a function defined in one file can be inline at a call site in another file. Here are some benchmarks. As you can see on the LLVM test suite, the performance can be sometimes really interesting. You may wonder about the top of the list. Those are single source benchmarks. So that doesn't line up with what I just said. There is no cross-module optimization that can go on when there is only one file. So there is a second part where LTO benefits. It's linker information. The linker will tell us about the list of symbols that needs to be preserved and that can be used outside of the LTO unit. The symbols that don't need to be used outside of the LTO unit can be internalized. So the optimizer can now assume that it sees all the uses of those symbols. So for a global variable, for instance, it's like making it static. And now we can benefit from more accurate alias analysis, and that enables better vectorization and better optimization in general. For function, we can change the ABI. We can optimize the calling convention, and we can remove parameters when they are unused at every call sites or constant for them. Let's see on an example how LTO gets those benefits from those information. So on the right side, you have a global variable that is static to this file, and it's initialized to 0, but can be set to -1 in foo2. In function foo1, we test the value of I, and the test is true only if foo2 is called before foo1. The optimizer cannot do much, usually in this case. During LTO, conceptually, we are merging those two files. And that happened on the IR, but I show you see here for convenience. Now, with linker supplied information, we're going to be able to turn most of those functions into static functions. If you build a binary, you only need to preserve main, usually. So those other functions will become conceptually static. And now when the optimizer builds the call graph, we start in main. Main calls foo1, which calls foo3, calls foo4. And you notice that foo2 is never reached, so it can be just deleted. And I becomes never written to, it becomes a constant, and we can constant for the test. The test will always be false, and we delete the test and the calls to foo3. Foo3 becomes in turn unreachable and can be deleted, and foo4 as well. So we end up with this code where we can now constant fold and inline foo1 into main, and main is fully simplified, and we can delete foo1. And that's the code that will go to the codegen. So LTO is very powerful, and everyone should use it. but unfortunately, the adoption is still very low. Over 10 years after its implementation in LLVM. And one of the main reasons is that LTO is slow. It's slow because it's serial. All the link will be single-threaded. So building Clang on a modern machine can be done in 4 minutes. But with LTO, it's going to take 16. With Incremental Build, it can be even worse. You may be used to just change one file and rebuild Clang. And that's a matter of a few seconds, because the final link is almost immediate. With LTO, you have to pay the price of reoptimizing the full program, and it takes over 12 minutes. Some people can take advantage of this quite efficiently. But let's move to the last point, which is memory consumption. The memory consumption can be huge because all the program has to be optimized in memory at the same time. So a few releases ago, linking Clang with LTO consumed over 40 gigabytes of memory with Debug info. And Debug info representation improved a lot over the last few releases. And despite those improvements, the trend shows that we reached the limit of what we can improve with the current model. We are kind of at a dead end. As of today, despite those improvements, Chromium cannot link. With Debug info, it crashes after 2 hours of processing and over 50 gigs of memory. So we need to address those issues. We need a solution that would be parallel, incremental friendly, and memory lean. And we need all those 3 key points to be at the core of the design if we want to reach our goal of enabling LTO in your production builds. Let's see if Teresa is up for this challenge.
So a couple years ago, in order to get some of these key features that Mehdi talked about, we started designing a new approach for scalable link time optimization because we wanted cross-module optimization that would scale to some of the huge applications that we need to optimize well for running in Google's data centers. And so we do this via, with ThinLTO, having fully parallel compile steps, as well as fully parallel backends. And this is the key to enabling distributed builds that can actually distribute a lot of the compilation. And as we'll describe later, this is made possible by having a very thin serial synchronization step between the compile and the backend. Additionally, with this model, because the module is still the unit of compilation all the way through, this enables incremental builds, because now we have something we can cache that's much smaller than the entire program. And another key insight was that for effective cross-module optimization, each module really only needs to see a small part of the rest of the application, for example, for inlining. And so what we've done is, with ThinLTO, we only perform profitable cross-module optimizations into each module, and this limits the memory overhead and improves the memory scaling. Okay, so how do we do this exactly? Like a regular LTO build, with ThinLTO, we generate bitcode when we compile. But in addition to just the IR's bitcode, we generate a small summary that goes with each module. It's in the bitcode, but it's designed to be separately loaded, and it describes the functions and the variables defined in that module. So now when these modules or these bitcode files are passed to the linker plugin, instead of reading all of the IR and merging it all, we only read the summaries out and aggregate them into a big combined index. This is very fast because we don't need to parse any of the IR. The bitcode files are then sent to parallel backend threads, and using the information in the combined index that's generated by the ThinLink, which tells us where different variables and functions are defined, we can actually simply import the functions that we want to, for example, inline into each module in the backends, and drop those functions after inlining. Then these modules go through the rest of the normal optimization pipeline and codegen, and finally, the native objects are linked. All right, so we have a 3-step process, the compile and the ThinLink and the backends, and let's walk through each one of those. As Mehdi showed earlier, when we normally compile, we would normally generate native object files. But when you pass -flto, you get bitcode. If you pass -flto equals thin, in addition, you get this small summary. And so what I've shown here is an entry in the summary for each function defined in that module. And along with the function name, we put a small amount of summary information that can be used to make importing decisions without looking at the rest of the IR. So for example, the number of instructions in each function. Additionally, if you have profile data, if you've collected profile data with the prior training run and you feed that back, we'll put some summary information in the, some profile information in the summary, and we'll show later how that's used. And you could potentially put other attributes in there as well. So when we get to the thin link, and these modules are passed, we generate this combined index. And as I said, it's very, very fast. It's less than a second for climbing, because while it's sequential, all we're doing is reading out these summaries and aggregating them. So we read the summary from main, put it in the combined index, note where the module it was defined in is located. And one thing to note is that we drop the original function name and replace it with a hash. This is not only more space efficient, but more importantly, as we'll show later, this is the same hashing scheme used to encode information about that function in profile data. And that will enable us to do better profile-based optimizations in ThinLTO mode. So we walk through the rest of the modules and build the combined index. Okay, so now the backend, actually what I'm going to step through first is how we originally designed the ThinLTO backends, specifically with how function importing is done. And this is what was first implemented, and I'll talk through that, and that we'll kind of get to why and how this evolved into our current model. So in the backend, still today, we do cross-module importing, and then the rest of the optimization and code generation pipelines. And the way that we would do importing was when we're compiling main.o in its backend thread. We parse its IR, of course, because we're compiling it. And we look for calls to functions that are defined externally, compute the hash, and look it up in the combined index, see that it's defined in test1. So then we lazy load test1. And by lazy loading, I mean that we're not parsing all of the IR, we're simply kind of building up the symbol table. And we only need to parse the function that we want to link in. So we then go ahead and link that in. And you'll note that when we import this into main.o, we give that imported function available externally linkage. This is a special linkage type that tells the optimizer that you can drop this function after inlining is done. So then we now parse the newly linked in code, find another external call, look it up. It's in test2, lazy load it, parse the function, and link that in. Now again, we recursively look at the IR here, find another external call, look it up. And this is defined in test1.o. So now we re-lazy load test1.o, parse that function and link it in. And there's a trade-off here between the cost of reloading test1 versus the memory overhead we would have if we had just kept it in memory during the whole function importing process. And so now Mehdi's going to talk about our experience with using this.
So ThinLTO was proposed at EuroLLVM with this model, and after a few RFCs on LLVM dev, we implemented it upstream. And last year, in December 2015, we had Clang that was bootstrapping on macOS after we had the linker support part. And so that was a good accomplishment. We had a solution at this point that was parallel, incremental. If you hash the IR after importing in the backend, you can query a cache and stop it without optimizing and code gen. So that was somehow incremental. It was also memory lean because the backend processes only one file, and you don't have to put the full program in memory. So great, we were quite happy and left for vacation, and we were done. Well, we wouldn't be here if we were done. So when we came back, we noticed that the link time was really terrible on a single machine. And the reason is that the importing alone was taking over 3 times the time of monolithic LTO and the full optimization and code gen of monolithic LTO. So it did not really matter for the prototype they had at Google, because when you have an infinite number of machines, you can absorb the overhead because this overhead was fully parallel. But on a single machine, you need at least 4, 5, or 6 threads before even catching up with monolithic LTO. The reason was when you try to link opt, you feed the linker over 1,000 files. But it was resulting in over 30,000 loads of the IR. And parsing the bitcode and creating IR is really slow. And with debug info, it's even worse, because debug info are not lazy loadable. you have to load them for the full file. Even if you want to import one function, you cannot get just the debug info for this function. And we still have today some limitation on this aspect. So some people more experienced in the community told us that you cannot get an LLVM component good enough until you have rewritten it at least once. And we didn't believe it, so we just moved on and tried to optimize the implementation we had and optimize the hash map, the hash function, trying to vectorize everything. And we got some nice, maybe 10% improvements. And we realized that we would better listen to Chris and take his quote from this chapter of this book and start re-implementing ThinLTO and redesigning it. That's what we did for the next few months, and that's what we're going to show you now. So let's look back at the big picture. So the big picture of ThinLTO is going to change a little bit. First, the compile phase is going to be extended. We're going to add call graph information in the summaries. We're also going to hash the module, and that's going to help the incremental build state. During the thinning phase now, the summary is going to get bigger. We're going to have the full call graph for all the LTO units. On this, we can run interprocedural analysis and produce some results that are going to be sent to the parallel backend where they will be used to perform the actual transformation. So that's the new model. Let's start with the first phase, the compile phase, and let's see what changed. So that's the example we had before. And now we're going to look at the IR and find all the references of a global or the direct call to other function, and we're going to store them in the summaries, along with other information that are useful when you want a call graph, like the linkage information. So we serialize those in the summaries, and we're going to benefit from those during the thinning phase. So the thinning phase starts. We have the combined index, and we extend it with those new information. And because it's combined for all the LTO units, we have now a call graph that span across modules. And we're going to process this call graph and perform some analysis over this call graph using the summary informations. So now we have a serial phase that has taken some more responsibility, so it's going to be a little bit slower. But it's still very fast because we don't touch the IR. We don't have to create any module. So it's still very fast, a matter of a few seconds for Clang. So let's see how the importing scheme changed.
OK, so now that we have this full call graph in the thin link, we can walk it at this point instead of waiting until the back ends. And we can build up import lists for each module. So for example, for main, we'll decide that we want to import those same 3 functions. We put their hashes into the import list for main, and we note where those are defined. And we do the same for all of the modules. So now when we get to the back end, we simply, when we're compiling main.o, we read its import list, and we now can process and link in all of the functions that we want to import from each module at the same time. So for test 1, we only need to lazy load it once, and we materialize those 2 functions, and we link them in, and then we move to the imports from test 2. And having this information up front addresses the overhead that Mehdi talked about with having to load so many times. Now we're only loading each module at most once. OK, so now let's say we've imported those 3 functions into main. Now we go into the rest of the optimization and code-gen pipeline. And one of the first things that's done is the code-gen SCC passes. And that processes the call graph, or sorry, I said code-gen, I meant call graph SCC passes. And that processes the call graph from the bottom up. And the leaf of this call graph is one of the imported functions. So we perform all the simplification passes on that. We walk up the call graph to its caller, see if we want it inline, simplify again, and so on all the way up until we get to the root of the call graph, which is main. Now, if we've done our importing right, we would have hopefully inlined all of these functions up into main, because the next thing we do is we drop all of the available externally copies that we brought in. And so if we hadn't inlined, that's a whole lot of wasted work. So we really want to have the importing heuristics somewhat in sync with the inlining heuristics. Then we go through the rest of the optimization pipeline, code-gen, and generate main.o. Now, at the same time, in another thread, we're doing the same thing for each of the other modules, such as test 1.0. So we import into that, optimize code-gen. And you'll notice test 2, the function test 2, which is imported here into test 1.0, is now being compiled and optimized 3 times in its original module, which is test 2, and in both main and test 1, which both imported it. So there's some redundant work here, but the redundancy is what enables this full parallelism in the ThinLTO backends. Okay, so now rewinding a bit to the thin link stage. As Mehdi mentioned, because we have this full reference and call graph, we can do a number of interprocedural analyses during the thin link. And the first one I want to talk about is actually required for correctness when you do importing. So if we focus in on test 1 and test 2, and let's say we added a static function bar into test 2. Now, when we're compiling test 1, we import from test 2, and we do some inlining, and eventually we end up with now a call to bar from a different module. And this is obviously going to cause a problem at link time because it's a static function that has local linkage. And so what we need to do is promote any local functions or variables that are referenced externally due to an import. And what we can do is, because we have a full reference and call graph at that thin link time, when we're walking that to figure out our imports, we simply keep track of what local values are exported as a result of any importing, and we mark that in the index for promotion in the backend. Another thing we need to do is rename it, because once we promoted bar to global scope, it might actually, the name might conflict with a global bar that already exists, or another static function bar that exists somewhere else, maybe in the importing module. And we also, because we're compiling test 1 and test 2 completely independently in the backends, we need to make sure that the renaming is consistent between those two, but they can't really, they're not talking to each other. And so we leverage the module hash that Mehdi mentioned we now add in the summary for each module. It's used for incremental builds, as we'll show later, but it's also, we can simply take the module hash of the defining module, test 2, and in each of the backends, when we mark something for promotion, we append that to the name. And so next, Mehdi is going to talk about some of the other interprocedural analyses that we do during the thin link.
So another analysis that we do is to deal with mostly C++ templates. And so as you can see on those examples, we are using a stud vector in those two files, and we're calling pushback. So the template is going to be instantiated in those two files, and the result is that we're going to have a pushback slow path function that is not going to be in line in none of those modules because it's too large, but it's still going to be present. So it's going to be optimized in every file that's called pushback separately, and it's going to be cogen also in those files. And so that's a lot of redundant work. Monolithic LTO get it right naturally. By merging all the bitcode files together, it will do the same thing as what the linker would do. Pick only one instance of it and optimize it and cogen. That's very efficient. ThinLTO is going to do a little bit more work because we are not merging the files together. We need to use the index to find the duplicate copy and mark them as available externally so that they can still be in line, but they won't be optimized and cogen in the later phase. And only one of the instance will be marked as preserved and will be cogen. That's fairly effective. When we look at Clang, it reduces by 25% the total number of functions that go to cogen. And that helps compile time. Let's talk about another analysis that we do, dead global pruning. On this example, on the left, you have a single global variable, and you have a getter. In the other file, you have a setter for this variable. In the combined index, we get all the globals and their relation. Now, when you link this code to the rest of the program, assume that this option is never used. It might be a debug option, and you're building a release build. So the linker will tell us that the setter is never referenced, and we mark only the getter as preserved, and we can start to compute reachability on this graph, starting with the linker supplied information. So option is reached, and the rest of the graph can be pruned. So we're going to remove the setter. And we haven't performed any IR transformation at this point. We only process this conceptual call graph. And this analysis is more an enabler for future analysis. By reducing the size of the graph, we're going to produce smaller import lists. So all the importing is going to be helped, and we're going to promote less variable to global scope. It can also help to internalize option into the module and constant folded. So we have still some limitation with global variables that I'm going to show you now by taking the same example I took at the very beginning to show monolithic LTO. So that's part of our future work, and we know how to improve it. So let's look at how this example ends up with ThinLTO. So when we cogen, we're going to import function into main and inline, and we're going to inline perfectly, but we don't eliminate the test as monolithic LTO can. This is because I is defined in another file and now has global scope. So we don't know that it's a constant in practice. That's the code that will be generated by ThinLTO today. If we extend the summaries with more information, like the constant ranges, it would enable to fold these tests and to catch up with monolithic LTO. The other file that will be processed in parallel by ThinLTO will contain foo3 and foo1. And those functions are never used. They're going to be dead stripped by the linker. However, because we are processing in parallel, we don't know that they have been inlined into main and that they are no longer needed. So there's still a little bit of redundant work that is done here. But that's what enables the parallelism. And so that's just one example. And we have other information that we need to add to the summary to catch up with monolithic LTO entirely. And that was so the IPA that we are performing. And now we're going to see the profile-guided optimization.
Great. So I mentioned earlier that when there's profile data available for the compile, like if you've done a prior instrumentation and training run, we can take advantage of that in ThinLTO. So one important type of profile-guided optimization is indirect call promotion. If we had a, let's go back here. If we have a indirect call, for example, to bar, which is a function pointer, when you profile this, it will do value profiling of the indirect call targets. And when that profile data is fed back, if the optimizer sees that there is a particularly hot target for an indirect call, it will perform indirect call promotion, which essentially means we insert a guarded direct call to that hot target with a fallback to the indirect call in case the profile data was wrong. However, this only works if the target is defined in the same module. So if we split this instead into two different modules where the target is defined in one and the indirect call is in another, and now at O2 we can't do indirect call promotion here. But within LTO, we can actually remove this constraint and optimize indirect calls across module boundaries. Okay, so how do we do this? When we are generating the summary for the module containing the indirect call, if we are passing back profile data via -f profile use, there will be a value profile metadata attached to the indirect call, and it encodes the hot target. And now this indirect target is actually encoded with a PGO function name hashing scheme. This is the same scheme that I mentioned earlier back in the combined index is used to represent or encode the function names in the combined index. So we take advantage of that here. We can simply speculatively insert what looks like a direct call into our summary for that function. And now when we get to the thin link, we build our combined index as normal. We end up with this call graph. And this indirect call looks like any other call in the index. And so the importing proceeds normally and can select that indirect call target just as it would a direct call target. And if we do import that, now the indirect call target is in the same module, and we run another round of indirect call promotion. We can promote it and hopefully inline it, which is where you get a lot of benefit from indirect call promotion. And now Mehdi is going to talk about some other uses of profile-guided optimization.
All right, so the second case where profile data integrates with ThinLTO is for the importing decision. So if you look at this example on the left, you have a function foo that can call a hot function or a cold function. And statically, you don't know, but at runtime, obviously, the hot path is going to be the hot function. So if they were in the same module, the inliner, which doesn't know about which one is hot or not, is going to inline only the cold path, because it might be a smaller function than the hot one. And ThinLTO would do the same. It would import only the cold function, because that's the one who is likely to be inline. So that's unfortunate. We are optimizing for the cold path, and that's not what we want. So if you have profile data, now you know which edge, which call is the most important to optimize. And the inliner knows that and would inline now hot and not cold. So that's great, but we need to adapt this to ThinLTO. So we propagate the hotness information in the summary, and we decorate the edges with this information. And so now ThinLTO importing is kind of mirroring the inliner heuristic and will import the hot function and not the cold function. And we are going to be able to optimize the hot path. And so that was the integration of profile data with PGO. Now I'm going to talk about incremental build. So we need to revisit the compile phase. And as I mentioned earlier, we're going to add a hash of the module. While we emit the bitcode, we are hashing the bitcode content itself. And at the end of emitting the bitcode, the last thing we emit is the hash of the module. When we reach the thin link, we have the combined index that will now contain those hashes for every module. So we know the content of the input files. We're going to generate import lists as before, but now those import lists will also contain the hash with each module we are importing from. So those import lists are going to be sent to the backend. And the backend, the first thing it does is reading the import lists, but now it can compute a unique hash of just the import list itself. And because the import lists contain the hash of the content of the files, this hash alone identifies the computation that the backend is about to perform. So we can use this hash to query a cache and try to see if we already built this object and return it to the linker immediately if it's the case. And we do this without loading any IR. So that's how we get a very fast incremental build, hopefully. If there is a cache miss, we just process as normal. And when we're done with the object, we commit it to the cache before returning it to the linker. It's worth mentioning that the final link that is performed by the linker is not incremental. We always return all the object files to the linker, and the final binary is always fully generated. Microsoft Visual Studio, for instance, has a mode where they can incrementally link in place and update in place the final binary. They are able to identify only which function needs to be cogent and replace it in the final binary. However, this has the disadvantage that the final binary is going to be always different. With our solution, even though it's coarser grain, it has the advantage that the final binary is always bit-to-bit identical, despite if you do an incremental build or a clean build. So that was incremental link with ThinLTO, and Teresa is going to talk to you about distributed mode.
At the beginning of earlier in the talk when I first introduced ThinLTO, I mentioned that one of the things we really care about in Google is having effective distributed builds. We use a distributed build system, and we have really large applications that rely on that to get decent compile times. So to get ThinLTO to work in a distributed build environment, we take everything that is done in the in-process model in the linker plugin, and we split it apart into different processes. So the thin link is a process that's executed somewhere, and then each of the parallel backends is now a separate process that can run on a different remote build node. And to do this, we need to stream out the analysis results. And so we stream that out as a small bitcode file that has like the summaries for the module that we're going to compile, and also the summaries for anything that we want to import. And we also stream out a small text listing of the other bitcode files that we're going to be importing from. And this is given to the distributed build system so it knows which bitcode files to package up for each and send to each remote node. So with that, we can then launch these jobs, pass the analysis result for that module, and pass in all of the bitcode files that are needed for that module's compilation. And we can then do all of these interprocedural transformations on the back end based on this analysis results. So compile the module and do the importing using the data in the small index file and importing from those bitcode files that we sent to the remote node. And then each of these jobs produces a native object, which is then fed to a traditional native link. Another thing I wanted to note is that these individual index files that we stream out with the analysis results contain all of the information necessary to make incremental build decisions about whether any given backend job needs to be redone. Okay, so that's basically a summary of what we're doing, and now we wanted to talk about how this actually performs, and we'll start by talking about build time performance.
So let's see how it performs in practice, because we also thought that we were done the first time. So what about the second time? So when I link Clang, so that's just the link time of Clang on a particular machine. It takes about 20 minutes. ThinLTO with one thread only is a bit slower, 25%. And that's not surprising. We explained that we do a bunch of redundant work. And we also take advantage of the scaling to add more optimization passes that are run during the link. The important thing is how it scales. And starting with 2 threads, it begins to be a lot faster than monolithic LTO. And this machine has 16 cores. So when you reach the native parallelism of the platform, you have a 15 times speed up over 1 thread. And it's 12 times faster than monolithic LTO. Let's look at the memory side now. Memory side is a pain point of LTO. And ThinLTO reduces the consumption with 1 thread by 17 times. It scales quite well. Only 40 megabytes per extra thread. And when you reach 16 threads, it's still 5 times more efficient than monolithic LTO. Let's talk about debug info now. So line tables only is an intermediate debug info mode where you have rich stack trace, you get the location, but you cannot inspect the value of variables. So it's kind of an intermediate mode that adds a little bit of overhead on the build time and quite a lot of memory overhead for monolithic LTO. For ThinLTO, we have the same build time overhead, but we are containing the memory consumption. And it scales in the same way as a release build. Great, 7 times more memory efficient than monolithic LTO. Now finally, the full debug info mode. So that's really where monolithic LTO reaches its limit. As you can see, the memory explodes with over 17 gigs. And the build time is quite impacted. And I told you we still have some limitation with debug info because they are not lazy at this time. So ThinLTO is going to suffer on the build time, but it's going to contain the memory quite well. We are now 30 times more efficient in the memory side than monolithic LTO. The scaling is not as efficient because of the non-laziness, but still we consume 4 times less memory than monolithic LTO with 16 threads. So those are quite good results. And but that was Clang. And our goal is to scale on larger applications. And Teresa is going to show you how we scale.
Also, one of the things we wanted to do was compare against other LTO implementations. And so we wanted to compare against GCC's LTO implementation. It's open source, and we know that GCC has been doing a lot of tuning over the past several years to try and reduce the overhead of their LTO implementation. They have reduced the overhead when compiling things like Firefox, for example. So GCC's LTO implementation is called Whopper, and it has 2 parts. It's divided into, first, a serial whole program analysis phase that makes all the IPA and the inlining decisions. And at the end, it rewrites out partitioned IR. And those partitions are then compiled by parallel backends called LTrans. And the parallel backends do all the inlining within the partition and then the rest of the optimization and code generation. OK, so we can compare the ThinLink, which is our serial step in ThinLTO, against WPA, which is serial, and the 2 parallel backend LTrans to ThinLTO backends. And as Mehdi mentioned, we also wanted to look at how we scale with increasing input size. So in addition to Clang, we looked at Chromium, the web browser, and we also took an internal Google application that runs in our data centers. So comparing how large these are in terms of the IR, you can see that particularly with debug info, Chromium and ad delivery are quite a bit larger than Clang. And contain a larger number of files. But what's more important for determining how complex the IPA is going to be is how big the graph is. So we looked at the size of the reference and call graph in the combined index. And what I'm showing here is the number of nodes. This is the number of global values, like global variables and functions that are defined in each application. And you can see that ad delivery, for example, is 10 times larger than Clang. But even more important is how connected are these nodes. And if you look at the number of edges, now you can see like ad delivery is 15 or so times bigger than Clang. OK, so the first thing we did was compare the serial step. So this is the ThinLink to GCC's WPA. And on the left, what I'm showing here is the peak memory for each of these applications. ThinLTO's, the ThinLink is not affected by debug info because we don't have debug info in the summaries. So I only have 1 set of numbers for ThinLTO. But for GCC, I'm showing both without and with debug info. And you can see that ThinLTO the peak memory does increase as you go to the larger applications, but it's pretty constrained. Whereas for GCC's WPA, the peak memory goes up quite a bit when you go to the larger applications, and ad delivery, we ended up killing it after 3 hours and more than 25 gigs. And so that's shown here, that we killed it after 3 hours. Again, ThinLTO takes more time for the ThinLink takes more time for the larger benchmarks or the larger applications, but it's still pretty reasonable scaling, whereas for GCC, it's going to start requiring more and more time. And just a quick note that LLVM's LTO can't compile ad delivery. It also ended up getting killed after a few hours and a bunch of memory. Okay, so now looking at Chromium's build, now we're going to look at the full LTO pipeline. So we'll look at both the serial phase and the parallel phase. And if you look at monolithic LTO, this is LLVM's LTO. No surprise, it takes quite a long time. This is without debug info. With debug info, as Mehdi mentioned earlier, it actually crashes after a couple hours and a lot of memory. For ThinLTO, what I'm showing here is for various numbers of available threads, parallel backend threads. And as you can see, as no surprise, the parallel phase time goes down with larger numbers of threads available. For GCC, the number of threads, the amount of parallelism is also the number of partitions. And for GCC, also the parallel phase does get faster as you increase the number of partitions. And GCC has done a pretty good job, actually, of getting the times down over what a monolithic LTO implementation can get. But if you look at the peak memory, for GCC, you see that this comes at a pretty big cost in terms of memory. In particular, as you increase the number of partitions, this requires a lot more cloning for that backend inlining, and the time or the peak memory requirements go up quite a bit. ThinLTO, because the unit of compilation is always small, it's always a module, the increase in memory as you increase the number of threads is pretty minimal. We also looked at ad delivery in the context of a distributed build. So in Google, we use a distributed build system called Bazel. It's open source, and it has ThinLTO support in it. And we looked at ThinLTO and O2 and how they scale with increasing numbers of distributed build nodes that are available. And you can see that ThinLTO actually scales very similarly to O2. It's a little bit slower, probably because we have that serialization point in the middle of the build, the ThinLink, but it's actually quite similar. And now Mehdi is going to talk about how incremental builds scale.
So I hope you are convinced by the scaling, but what matters for day-to-day development is how we integrate with the incremental build. And so when you build from scratch, from a clean build, Clang, and that's the time to run Ninja Clang from an empty directory on this machine, it takes over 10 minutes to build with monolithic LTO, and only about 4.5 minutes with either ThinLTO or non-LTO. So we are on the same scale here, and we still have a bit of overhead due to some limitation in the current implementation, and we know we can reduce this overhead and divide it by 2 at least. So now let's say you're modifying a widely used header. You change the dense map implementation. Well, you're going to have to rebuild. It's in Libs support in LLVM. You're going to have to rebuild almost the world. So no surprises. Every solution performs almost as a clean build. There's not much improvements, but they're on the same scale. Now, what's more interesting is when you change an implementation file. Let's say you fix a bug in its combine. So without LTO, you just have to recompile one file and perform the final link. That's very fast. You're used to that. With LTO, for those who tried, you still have to pay the full price of the final link, and that's over 12 minutes. And that's very annoying, unusable for day-to-day development. So the question is, now with ThinLTO, we still have to rebuild this one file, but at the link time, we have to read the summaries from all the files, build this index, build the graph for the full program, perform our interprocedural analysis on the full program, generate the analysis results. We're going to spawn as many threads as we have files, so that's over 1,000 for Clang, and those backend are going to check a cache on disk and check if the object already exists. So that's quite a lot of work and a lot of overhead on top of non-LTO. And we do this in 6 seconds. So that's the current implementation of incremental build with ThinLTO. So now we're going to move to runtime performances and see how it performs in practice compared to monolithic LTO. So we built the test suite, the LLVM test suite on x86, and those are the histogram of the results, and that's compared to monolithic LTO. So on the left, we have quite a few regression compared to monolithic LTO, and when we investigated those, most of them are due to benchmarks that are stressing out global variables, which is still a part where we have future opportunities. On the right part, we have some improvements over monolithic LTO. That might not be intuitive, but I mentioned it earlier, we are throwing more CPU cycle to the optimizer within LTO because of the scaling. So we can afford it, and sometimes it pays off. What about binary size? So binary size, we're not there yet. It's a bit of an increase compared to monolithic LTO. And the main reason is that we don't have as much internalization. And the new LTO API that is currently in work upstream is going to help catch up, we hope, at least half of those cases. But the good news is that we still improve the binary size compared to non-LTO by 2.6%. So that's with a good results. And now let's see how we perform on spec.
All right, so this is what I'm showing here is all the C and C++ benchmarks from spec 2006. And the baseline is O2 with profile data feedback. In fact, all of the configurations here have profile feedback. And so the yellow bar is monolithic, LLVM's monolithic LTO with PGO, and the blue bar is ThinLTO with PGO. And you can see that across the spec benchmarks, there's a kind of a wide range in terms of how much performance you get from LTO. And that's not really surprising because some of the spec benchmarks are quite small and don't really benefit a lot from cross-module optimization. But where LTO gets performance improvement, ThinLTO is getting almost the same performance improvement, and this is so far without a whole lot of performance tuning. As Mehdi mentioned, we have some future work in global variables, and we know that that's going to catch us up in a few places. But currently, the geo mean, as shown on the right, for ThinLTO is actually extremely close to full LTO already. Some future work.
So we have ongoing work upstream on a new LibLTO interface, and we hope that's going to help the optimizer on the code gen. That's work that is driven by Peter Koninborg.
We talked about how we use profile feedback to improve the ThinLTO in a few places, and we have some more tuning that we'd like to do in that area.
And Peter is also driving the effort to integrate with control flow integrity and the same framework that is used for LTO devirtualization.
For full monolithic LTO, there are some optimizations that are driven by function attributes, and we would like to encode that information in the summary so we can do similar attribute-based optimizations in ThinLTO.
So we showed that we have quite a bit of overhead, and part of it is due to the limitation of the current bitcode, and we need to improve it, make it faster to deserialize, and especially make the debug info lazy.
Another thing we'd like to do is see if we can get more internalization. So if there's a single call site to a function in another module, today we'll import it. We'd also like to mark it to be dropped in its original module, and then it can be internalized in the importing module.
And finally, our last opportunity for improvements that we identified is global variables. And we believe that by adding information to the summaries, we can get more improvements there. We can encode modref information or constant ranges and get the information we need to perform constant merge at link time. So we're almost done, but before moving on, I want to thank all the community and especially some people that contributed significantly to this effort. And Akira and Bruno helped a lot with the performance tuning and identifying where we need to catch up with monolithic LTO. Adrian and Duncan helped a lot improving the debug info, and Duncan helped a lot on a lot of brainstorming session. Peter Koninborg developed a new LTO API and is working on devirtualization and control flow integrity. Raphael was a lot of help on IRC on many aspects of this work. And Davide implemented ThinLTO in LLD, and that's going to ship in LLVM 4. And finally, Piotr did an internship to integrate PGO, and the results we've shown was due to this.
So in conclusion, we hope that we've showed you that ThinLTO scales like a regular non-LTO build.
We hope you're convinced that the performance can be very close to monolithic LTO.
And incremental builds, as we know, are very important to our day-to-day development, and we've shown that ThinLTO enables effective incremental builds.
So our conclusion is that we believe we set the path forward to reach our goals of replacing one day O2 with LTO during your production builds. Thank you.
Thanks.
All right, so I personally got very excited. Let's see if you still have some questions and doubts.
How do you guys handle static libs, .a's?
Say that again, sorry.
How do you handle .a's? Like the
dynamic
the middle,
libraries or static libraries?
Static.
Static?
Static libraries. So when you're linking static libraries with the indexing and all of that, how does that work?
Right. So for a static library, archive library, the archive in LTO mode, whether it's ThinLTO or regular LTO, contains bitcode, and the linker will basically unpack that. So and send the individual files. So if, for example, when you compile with Gold, it calls the Gold plugin for each member of the archive, and that's unpacked as a bitcode and then passed to basically handled normally. The one extension is that in the combined index, where we normally have a path to the object file, it would be an archive. So we actually have to tag that a little bit differently to make sure that we can keep track of which basically module within the archive that's defined in. It just pretty much then just works in the in-process model because all of those modules are passed in memory. Now, if you were to do this with a distributed build, the distributed build system would actually need to probably unpack the archive into a temp directory and send those individually. And
the only subtleties with archive is that when you build the archive, you need to have an AR that is aware that it needs to call LLVM. So the system AR on macOS, for instance, will use LLVM AR or will call LibLTO to do that. And otherwise, you need to use explicitly LLVM AR to create your static archive of bitcode so that the symbol table of the static archive can be built.
Hi, Sergey Laren from Qualcomm. Excellent work. Very impressed. One question. Not me. I might know the answer, I'll ask it anyway. Have you given any thought to mixing optimization levels within the same project? So if I have multiple files compiled with different flags, O3 to OS, how the LTO is handling that?
That's a good question. Do you have an answer?
Yes, we're given some thought, but we haven't reached a conclusion.
I said I almost know the answer.
It's complicated. The discussion is very complex. With monolithic LTO, it's already an issue because we merge all of these together, so there is only one single option. So for OS, it's not that much an issue because each individual function is tagged with an attribute, so the optimizer will honor this. If you would want one file with O0, you would have opt-none on the functions, and they won't be optimized. So that helps. But O2 versus O3, for instance, we cannot really handle that.
Some architectures have hardware flags encoded, so they might have different addressing modes or things like that. So I'm seeing it in my case, and I almost wonder if we need to think about propagating that information with the
we talked about this, about representing
right.
this in module attributes.
Right.
But there are some design trade-offs.
But it needs to happen for this to be turnable on by default, by the transparent for the customer.
Yeah.
Thank you.
Yeah. Can you tell a little bit more about the optimizations on the flags, right? Read only and stuff like this on the functions. Like what can be done here?
Okay. On the functions, yeah. So So with if you can mark the function as read only and we have a reference graph right now, but it doesn't say when we reference global variables, for example, whether they're being read or written. And certainly if we have that information and we put it into the summary, then we can do some of the optimizations that make use of that, knowing that a function doesn't actually write the values that it references, for example. And that was sort of related to some of the global variable optimizations that Mehdi talked about, putting that information in the summary. Did you have anything
Yeah,
to
there
add?
is also the function attributes, which is the main driver of interprocedural optimization in LLVM. If you know that a function only reads its arguments, for instance, so you can emit this in the summary and propagate this to all uses. Even though you wouldn't import the function, you can still decorate the declaration with those attributes.
All right, so I think we have last question.
Okay. Just a question about the optimizations that you think are amenable to ThinLTO versus monolithic LTO. I mean, do you see something like full interprocedural constant propagation as being like tenable, or do you think that there's certain optimizations like interprocedural alias analysis, a full interprocedural alias, that are just never going to be in ThinLTO?
There are definitely some limits. For instance, if you wanted to do interprocedural register allocation, which is very late in the process, it needs some synchronization at the code gen level, and that's definitely going to break the model. We thought about having multiple synchronization points by redoing a thin link after a few optimization, and you can iterate this way, but that has a cost as well, and so we don't know what the future will be there.
Yeah, and I think as we start exploring some of the global variable information and the attributes and some of those affect aliasing, we'll start to see, is there a cost to like really increasing the amount of information in the summary? Hopefully for a lot of the heavy hitters, and we can get that information in the summary and actually do that in ThinLTO. But there's going to be some trade-offs
So
as we
like
explore that.
you had mentioned mod references. I mean, like, to what extent would you be saving information about the mod ref? Just very simple stuff, or like a full summary of what's mod referenced in each function, or what?
We usually are driven by data and by benchmarks. So the first approach is to see where benchmarks could benefit from that and see what is the right level of information we need. But for instance, if we know that the address of a function or a global is never taken, this is the kind of information that can be encoded.
Okay.
And that's fairly cheap.
Thanks.
And just wanted to put a quick plug in there for the Hackers Lab, where we'll have an LTO table. So I'll be there. Hopefully Mehdi will be there. You can come ask us more questions.
All right, so let's close the session and thank the speakers again.